Hello class, this is CSE-5250, Section 60, Week 2, Fall 2023. I've made one update to the syllabus that I brought up during Week 1. This should have been in the syllabus, but now I've taken the time to update it on Canvas. When I say that your work has a 1-week grace period, that means your work can be submitted up to 1 week late from the original due date, and I'll still take it, but that doesn't apply to the midterm and final. Unless you've made arrangements ahead of time for a late submission, or you have evidence for an extenuating circumstance. So that's the one update to the syllabus that I've had to make. We're currently at Chapter 2 as the topic for this week. Though, in that chapter, it turns out the chapter is pretty thick, but at the same time, we don't really need to know all the information in that chapter, unless we absolutely need to know it. In fact, this is a long, broad chapter, so it may be a good idea to skim through some of the sections on a first reading so that you have a good idea of what's in the chapter. Then, when a concept or term in a later chapter isn't quite clear, it may be helpful to refer back to this chapter. In particular, you may want to skim over most of the material in the modifications of Neumann architecture except for caching. Also, parallel hardware, you can safely skim the material on interconnection networks. You can skim the material on SPMD systems unless you're planning to read the chapter on CUDA programming. I ended up including So as you can see, we have quite a bit of content in here. That includes your first short answer question for the course. Now, I am recording and uploading this video on a Thursday, so I have it so that the assignment, the short answer question, is due next Thursday. That is, today is September 7th, so that will be due on September 14th instead of what would be Wednesday, because again, I'm recording this on a Thursday instead. So there's 29 slides for us to go through. So let's start at the very beginning. Remember the von Neumann architecture? From, say, CSE 4010 or possibly earlier than that? We have two main parts, that is the main memory and the CPU, but actually a third part that connects the two together. It's called an interconnect. It's usually a bus. The CPU itself can be divided even further into a control unit, which is responsible for deciding which instructions to execute, and a data path, which is responsible for executing the instructions. We can go even further than that and break down the CPU even further down to an ALU, but for our purposes, we're just going to look at the control unit and the data path. Within the CPU are little pieces of memory called registers. If you recall the memory hierarchy from, say, CSE 4600 or 4610, you may recall that this is on the top of the memory hierarchy. It is the fastest piece of memory that the computer works with, but it can only store one word of information. Meanwhile, memory is often slower than the registers. In fact, in the time it takes for the CPU to execute several instructions, that's how long it would take for a read operation to occur on main memory. That's actually the point of the next slide, but how fast data moves between the two is dependent on the interconnect here, and that is called the von Neumann bottleneck. So what about that cache? The cache is a form of memory that it lies in between registers and main memory. It's faster than main memory, but it's still slower than registers. It can still hold way more. It can still hold way more than a single register, but it's nowhere near the capacity of main memory. If the CPU were to read, if the CPU wanted to get a value from some address in main memory, the cache what will happen is that value will be copied onto cache. But not only that, the values in the next 50 addresses, say the next 50 addresses after that, are also copied onto cache as one big block. That's based on the principle of locality. If you need something at a specific address, there's a good chance that we're gonna need something from the next address after that. If you've ever built your own computer, you may have noticed that we have 3 levels of cache: L1, L2, and L3. If the CPU needs something from memory, it's gonna go down the hierarchy of caches. If it finds what it's looking for, that's a cache hit. If it doesn't find what it's looking for and has to go back to memory, that is a cache miss. So that's one modification to the von Neumann architecture. Another modification is called multiple issue. Multiple issue processors replicate functional needs and try to simultaneously execute different instructions of a program. See this for loop here? We're adding values from 2 vectors together and storing it into a third vector, so xi plus yi, and we're assigning that value to zi. We can have one adder do all 1,000 elements in the 3 vectors, or we can have 2 adders. It's like that example of dividing the work between a professor and 4 TAs from last video. But here what we have is a hardware implementation of that. So, one adder does all the even numbered indices. Another adder does all the odd number indices. So, in the end, we will have done this for loop in half the time. And the key is to find instructions that can be executed simultaneously. And by that, there isn't any sort of data dependency. That instruction doesn't depend on the previous instruction, for example. We can also have the system take a guess. Speculation is where the compiler or processor makes a guess about an instruction and executes the instruction based on that guess. So, the computer can just do some operation z equals x plus y. It could, say, jump the gun and decide for itself, I'm going to do this instruction. This comparison operation here would be one instruction, but then this one would be its own instruction. So the CPU could just take a guess and pick this one to execute. But what if it gets it wrong? Well, speculation must contend with that possibility. If that's the case, the system should go back and assign the correct value. So, it turns out, say we end up with a situation where z was not greater than 0, so it has to go backtrack and assign the proper value. If z is greater than 0, w equals x, else w equals y. So remember what I said about how you need to have instructions that don't depend on other instructions? Consider this for loop. This is a for loop that calculates Fibonacci numbers. We can't calculate the next Fibonacci number without calculating the previous Fibonacci numbers before that. And we can't calculate those numbers without calculating the numbers before that. All the way to the two seed values of f0 and f1, both equaling 1. So in this case, we cannot parallelize this for loop at all because each successive loop iteration requires the results of the last one. Instruction level parallelism may be hard to exploit, especially in situations where there is a long sequence of dependent statements. Thread level parallelism attempts to divide parallelism through the simultaneous execution of different threads. This could be coarse-grained, simultaneous execution of different threads, or fine-grained, simultaneous execution of individual instructions. SMT is a technology that you may have seen for yourself before. You know how you get a CPU and it's, say, 4-core, 8-thread? That is called hyperthreading, or rather it's branded as hyperthreading on Intel CPUs. So what happens here is SMT is a variation of fine-grained multithreading. So we have multiple threads making use of multiple functional units. SMT is a variation of fine-grained multithreading, exploiting superscalar processors by allowing multiple threads to make use of functional units. There is another way in which we get hardware-level multithreading, or rather, instruction level parallelism. That is called pipelining. I showed you an example of pipelining using that laundry example where you had so much laundry that you had to do it in batches, but you could do multiple batches sequentially, but at different stages of the laundry process. At the end of that example, we gave up and went to a laundromat because they had way more machines there. So yeah, that was an example of pipelining. There are other examples of pipelining. The most typical example the most typical example that is taught in the textbook is a factory assembly line where, say, it's cars on an assembly line. So a car will go through different stages in the assembly process, but at the same time there would be other cars on the same assembly line in different stages of being put together. There are other examples in real life that fit that description. Say, for example, one of those automated car washes. So, for example, you could have several cars waiting in line to enter the car wash, and then your car enters the car wash. At the same time, the car ahead of you is further ahead in washing, and the car after that is already having, say, tire shine applied on its tires, and the car after that is already being blow dried. You gotta make sure that the pipeline works, because if you have a situation where the car is somehow unable to move, the whole pipeline stalls, and then everyone else in the pipeline is gonna wonder, why did I stop moving? I know this from experience because I was the one who stalled the entire car wash. Moving on. Remember this diagram from last video? It turns out that's a diagram illustrating something called Flint's taxonomy for parallel hardware. I say hardware, but we have a fifth classification here that means single program multiple data. We'll look into what that means later on. For now, let's look at SIMD and MIMD. SIMD hardware includes, for example, GPUs. So, SIMD systems are parallel systems where an instruction is broadcast from the control unit to individual data paths, and then each data path either applies that instruction to the current data item or it's idle. So if we have, say, vector addition, we're incrementing the values of one array by the values of another array. If we have n data paths, we can load, say, the ith element of x and then the ith element of y into the ith data path, and then have the two values added and then stored back into xi. The idea is this: we can do a batch of n calculations in parallel. So it's like that previous example where this kind of thing was done on the hardware level. Here we're doing kind of the same thing in parallel. The fact that some data paths can be idle can pose an issue. So if we modify this code so that yi must be positive, then we may have some data paths that are idle while others carry out addition. I have another example for what I mean by some data paths being idle. Say I have an array with numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, and I have to do an algorithm on each individual number, and that is to determine whether that number is prime. One way we can do that is to consider the number n. Consider the number n. We're going to brute force this by dividing it by 2, 3, 4, ... all the way to the number n minus 1. If there is a number within this range that divides n without any remainder, then that number is not prime. If we go through the whole process of dividing n by all of these numbers and find that none of those numbers divide n, then we conclude that that number is prime. Let's consider this pair of numbers. Say one data path is calculating whether 9 is prime, and then the other one has to calculate whether 10 is prime. So the number 9, is 9 divisible by 2? Is it divisible by 2? No. Is it divisible by 3? Yes. The number 10, is it divisible by 2? Yes. And then in that example, it took 2 checks to determine that 9 was not prime, but then it took 1 check to determine that 10 was prime. Here's a worse example. What if it were the numbers 10 and 11? One data path starts its process of dividing 10 by all the numbers from 2 to 9. It starts at a number 2. Oh, it divides it cleanly. So 10 is not prime. But for 11, it has to go through all the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. None of those numbers divide 11, so 11 is prime. So for a data path processing the number 11, it would have to go through all of those numbers, while the data path for the number 10 just sits back, and it would just sit back and relax, knowing that it had completed its work early. So yeah, that's what I mean by some data paths may end up being idle. Or rather, that's one example of how you can get idle data paths. The thing is, in an SIMD system, the data paths must operate synchronously. Each data path must wait for the next instruction to be broadcast before proceeding. Furthermore, data paths, they don't have instruction storage, so they can't store an instruction so it can execute it later. So as you can tell from those few examples, SIMD systems are ideal for parallelizing simple for loops that operate on large arrays of data. Data parallelism. So what's a GPU do? Well, real-time graphics APIs use points, lines, and triangles to internally represent the surface of an object. They use a graphics processing pipeline to convert the internal representation into pixel information that you can display on the screen. How much data is that? Well, it's not uncommon to see, say, hundreds of megabytes worth of data. So for that reason, GPUs need to maintain very high rates of data movement, and to avoid stalls, GPUs use hardware multithreading. I think this is a typo. A few caveats related to GPUs. It turns out GPUs are a mix of both SIMD and MIMD. For the following reasons: current GPUs can run more than one instruction stream on a single core. GPUs can have dozens of cores. Each one could be executing an independent instruction stream. And GPUs can either use shared memory, distributed memory, or for the largest systems, both. That's just a few caveats. We won't be looking at CUDA programming until later in the course. So what's an MIMD system? That's multiple instruction, multiple data. These systems support multiple simultaneous instruction streams operating on multiple data streams. Each processor operates at its own pace, so we say it's asynchronous. And in many such systems, there is no global clock. In the previous example, you know how cartoons depict Viking ships with a drummer and rows of people operating a paddle, and then the drummer, every time the drummer hits the drum, everyone rows at the same time? That is SIMD, and the drummer is the clock. Here, we have no clock. So here, it would be more like the example of the professor and 4 TAs grading up 100 exams, where the 100 exams are evenly divided between the 5 of them, and each one grades things independently of one another. That all opens up the possibility of one grader finishing faster than the others, but that's the thing that can happen with an MIMD system. Every processor operates at its own pace, even if it means one is just slightly faster than the other. So the memory system of an MIMD system can either be shared memory, where CPUs all have to share the same memory, or it can be a distributed system where each CPU has its own memory, and that CPU memory and each CPU memory combination, they talk to one another over an internet connect instead. They talk to one another using messages, because by distributed system, it could be, for example, that the CPUs are entirely different computers, but they're all connected on a network. in a shared memory system, typically what happens here is we have sections of shared memory that all the CPUs use to talk to one another. So that's the hardware. How about the software? In terms of hardware, we have plenty of machines and devices that have multiple processors. Even our phones have they're multi-core now. It's interesting because I was browsing YouTube the other week and I saw a sponsored ad for a gaming phone. When before that we had gaming web browsers. And I thought peak gaming equipment was like gaming chair, gaming desk, gaming peripherals, and RGB lighting. Not unlike my keyboard. Or, say, my mouse. Yeah, I thought that was peak gaming equipment, but then came in the gaming web browser, Opera GX if you've heard of it, and then the gaming phone. How about software? Many programs out there are programs out there already. They can leverage multiple CPU cores. Microsoft Excel, Adobe Photoshop, Google Chrome are examples cited by the textbook. If you are a 3D modeler, you can add Blender to that list. If you are a video editor, you can add any video editing software that you use. Any sort of professional video editing software that you use, you can add that to the list. The thing is, there's a lot of single-threaded programs out there, and because we're not making any more significant advancements through hardware alone, we gotta turn to programming to get those performance increases. Say you have your favorite video game from like the early 2000s and it's still single-threaded, but we can't get any more. The thing is, we can't get any more speed ups because CPUs aren't getting any more faster. In the worst case, the source code for that program might be long gone. So you have to go through the arduous process of decompiling it, if we could even legally do that. But maybe you get lucky and there is a decompilation of the program available, and now it's up to someone to figure out how to parallelize the code, the decompiled code, in this theoretical example of having to turn a single-threaded program into a multi-threaded program if in the extreme case you don't have the source code anymore. We can't get any more performance increases through hardware, remember? We have Moore's law plateaued like 20 years ago. So, we turn to programming. Enter SPMD. Single program, multiple data. Here, a single executable can behave as though it were multiple programs by using an if statement. Here's how it works. Say a program starts running and it immediately forks into, say, 4 processes. They each all have the same code. But each process has its own unique process ID. 0, 1, 2, and 3 for our example. And remember, they all have the same code, but they're all running more or less independently of one another. They can talk to one another via message passing, of course, and we'll get into that later on. But this is 4 programs. 4 programs, and they're all operating. They all have the same code to execute, but they have different process IDs. It enters the if statement, if this is thread 0 or process 0, do such and such code. Otherwise, do some other code. So it's as though we wrote multiple programs in the space within the source code of just one program. Single program, multiple data. So how do we coordinate the processes / threads? One thing to keep in mind. We can do this with either processes or threads. As a recap, a process is a program in execution that the operating system has to manage. That's a process. Processes are basically standalone programs because oftentimes they are. They basically are. When we talk about threads, we are talking about portions of the same program that are concurrently executing or in parallel. So, a process can fork into one or more processes, and the processes themselves could be independent. A thread could fork into multiple threads, but they're all part of the same process. So that's the main differences between processes and threads. There are some other considerations, such as it turns out threads are easier to context switch than processes. But in either case, if we have a for loop that we want to parallelize, sometimes we can just get lucky. So lucky we call it so easy. Sometimes it's so easy we call it embarrassingly parallel. Here's what I mean. This add operation can be parallelized by dividing the work as evenly as possible. That's called load balancing. If we have, say, 1,000 elements and 4 threads, for example, one thread gets the first 250 elements, the next thread gets the next 250 elements, and so on. That's something that is embarrassingly parallel, as I said. So here's the steps for how it's done. 1. Divide the work so that each thread gets roughly the same amount of work. That's load balancing. And the amount of communication required is minimized. The next two steps are often interrelated, but arrange for the threads to be synchronized, arrange for communication amongst the threads. So, when you have processes or threads, doesn't matter, they both follow a fork and join model. So, say one process forks into multiple processes. Those processes have to talk to one another, but after that, say it's load balanced, they do this operation, and then all the processes join back together and combine the results together into one array. Because this is something that because this is an operation where we have to have those results in one array and not divide it into 4 different arrays. There are a few dangers to consider. If multiple threads or processes attempt to simultaneously access the same shared resource, we get a condition called a race condition, sometimes called a race hazard. It's called that because processes are literally racing to the same thing. And in a race condition, last place wins. Think about that for a while. In some cases, we need to make it so that only one process or thread can access a block of code at a time. If we do that, we will have created a critical section. And it's our jobs as programmers to ensure mutually exclusive access. Basically, one process at a time is allowed. We typically do that with a lock. So, one process acquires the lock, enters the critical section. No other processes are allowed into that critical section until that process exits the critical section and releases the lock, and then the next process can go into the critical section. There's one other thing that's worth talking about, and that is Amdahl's law. This is a formula for calculating the potential performance gains from adding additional cores to a parallel program. In the execution time of a program, you're going to have some time that is parallel and then some time that is non-parallel. So, what these numbers are here? Well, S is the proportion of the program that cannot be made parallel. So that's the serial part of the program. That's going to take some time, and we cannot change that time at all. 1 minus S is the proportion of the program that can be made parallel. One way to think of these values is to think of S as being a percentage from 0 to 100%. But if we do that, we need to replace this 1 here. Excuse me. One way to, as I said, we can think of S as being a percentage instead, but we have to convert this 1 into 100%, and then we have to do some percentage conversions. Typically, the value for S is some number between 0 and 1. So we say S, so therefore, 1 minus S is actually another value, let's call it P, and that's the parallel part. The parallel part will also take some amount of time. But we can divide that time by X, and that is the number of CPU cores that we use. So here's a super duper simple example. S is 0.5, so half of the execution time is non-parallel code. That means 1 minus S is parallel code, and then that takes up another 50% of the execution time. If we add just one additional core, so instead of 1 core we have 2, then we will have reduced the execution time by 75%. And that translates to, I believe, a 1.3 times speed up. There is a way of visualizing this, so I would have to take out a drawing program again. Give me a minute. Alright, so we're back here. Let's consider the example of the program having 50% of the runtime is non-parallel code, but 50% of the runtime is parallel code. What we do in the case where we have 2 CPU cores is this. We cut this in half. So now we have 50%. And now 25%. Typically, the last few times I've thought about this, I envisioned stacking the blocks on top of one another. That way we represent the same amount of work being done in less time. So now we have a program that used to take up 100% of its execution time, now taking up 75% of its execution time. But the thing is, we get a percentage of the reduced execution time. But we want to convert that into a speed up, so we have to do 1 divided by 0.75, and that is what? Let me get a calculator. If I get a calculator and quickly punch in 1 divided by 0.75, it's a 1.3 times speed up. This block diagram assumes that all of the non-serial this block diagram assumes that all of the serial parts happen as one huge code block, and then all the parallel part after that is also one big code block. or rather time block, I should say. This represents time, not code. Thing is, in an actual program, you can have serial and parallel parts just peppered in amongst one another. More like this. So this is an idealized representation of a parallel program's execution time. Think about what happens if we kept adding more and more CPU cores to this one particular problem. If you think about the limit, then at some point, this 50% block will be divided into so many pieces that we would have, say, barely anything left, because so much of the work is being done in parallel now. We would say that the execution time approaches 50% of the original execution time, because we can't get this 50% part any faster. So the maximum theoretical speedup for this program here is 2 times speedup if we were able to add more and more CPU cores to it. This is an idealized example, of course, because one thing we at some point the instructions will reach an atomic size, and by atomic we just reach one instruction, so we can't divide it any further. And another thing, there's also the overhead of parallelizing it in the first place, the overhead of forking and joining so many processes. So Ohm's law is idealized in that it doesn't account for overhead. The textbook shows Ohm's law in a slightly different way. I like this way better because it's a little easier to understand. But yeah, those are just the basics of chapter 2. And with that, we enter our first short answer question. This is problem 2.10 in the textbook on page 85. I just basically copied it directly from the textbook. So there you go. Under Flynn's taxonomy, we have SISD, SIMD, MIMD, and SPMD. We didn't really look at SISD because those are just serial programs. But the one thing that we also didn't look at is MISD, or multiple instruction single data. How would such a system work? You can look this up online to help you find an answer, but if you do, I would recommend citing your answers. Of course, you can always turn to Wikipedia, but if you want to go to Wikipedia for that, cite the sources that Wikipedia cites. So yeah, that's your short answer question. As I said, this is due on Thursday, September 14th, because I'm recording this on a Thursday. Alright, so that's going to be it for this week. From here on out, we're going to be basically having one video a week, because now we're going to be looking at programming, and we're going to be starting at chapter 5. Alright then. Shared memory programming with OpenMP. OpenMP is an API for shared memory MIMD programming. The MP stands for multiprocessing. So we have a shared memory system, as we just saw in chapter 2 already. We're going to start programming next week, alright? So with that, I'm going to end the video here. If you have any questions, feel free to email me, and we'll pick up next week where we start programming. I'll also have like instructions on how to set up your computers for OpenMP programming. Because depending on what kind of computer we have to program with, you may need to turn on a few additional settings, or possibly you may need to remote access the Jack Brand Hall labs just so you can, actually work on some of the programming assignments. Alright, that's gonna be it. See you next week.